This is the first problem we are having it. One dimension harmonic postulation. The minimum time after which the oscillator will be found in same state. So psi t would be 1 by 2 0 e to the power minus I a0 t by h cut plus 1 e to the power minus I a1 t by h cut. We have to determine the time period after which this form would reduce to 1 by root 2 0 e to the power minus plus 1. This can only happen when e to the power minus a0 t by h cut is equals to 1. Similarly, e to the power minus e1 t by h cross is equals to 1. We divided 1 by 2. That means e to the power minus I a0 t by h cut is divided by e to the power minus I a1 t by h cut is equals to 1 implies e to the power I a1 minus a0 t by h cut is equals to 1. And that can only happen when e to the power I a1 minus a0 t by h cut is equals to e to the power I 2 pi. So t would be 2 pi h cross by e1 minus a0 2 pi h cross into and 3 by 2 h cross omega minus 1 by 2 h cross omega. So t would be 2 pi h cross by h cross omega give us 2 pi by omega. Now, in this problem, we have been provided 3 shapes of the potential well, and question is asking determine the correct ordering for energy. This problem can be solved very easily. Now, we know it. The particle of infinite well is always having energy greater than the particle of half infinite well. That means EC would always be greater than EB. Now, is this condition available in any of the given option? Let us check it out. In the option B, EB is greater than EC. In the option D, EB is greater than EC. And in the option C, EB is greater than EC. So there is only one option in which energy EC is greater than EB. So our option A is correct. Don't require solution for such kind of problem. This is in this problem. Initial state is Jy and it is rotated along positive y direction in along positive y axis in counterclockwise direction. So the rotated state or psi phi would be given by. Let us assume psi phi state would be given by r y theta into psi I. Now initial state ry theta minus I epsilon jy h cross and initial state is j0. Now the question is saying it's up to normalization constant. That means we can simply expand the exponential term 1 minus I epsilon jy by h cross into j0 state. This can be written as j0 minus I epsilon h cross jy into J0. Now we also know it. Jy can be written as J plus J plus minus J minus divided by 2y. So substituting this value we get J0 minus I epsilon by h cross to J plus minus J minus divided by 2y, which gives me J0 minus epsilon by h cross twice J plus J0 minus J minus J0. Now the value of J plus minus Jm is given by h cross root over J minus plus m into J plus minus m plus 1 into J and straight m plus minus 1. Since m is equals to 0, so J plus minus J0 would be equals to h cross J into J plus 1 into J into plus minus 1. Substituting this value in this equation, we get psi phi is equals to straight J0 minus epsilon by 2h cross into h cross J plus 1 to J plus 1 minus h cross into J plus 1 into J minus 1. That means J0 minus epsilon by 2. We can take it common. J into J plus 1. We would be having straight J plus 1 minus J into minus 1. So that is psi f. Checking the correct option would be option B. This question is related to hydrogen atom, and here the question is asking determining the wavelength for hydrogenic atom with Z is equals to with having nuclear mass this. Wavelength for the first Balmer line is given. So wavelength for Balmer line is line for H atom is given by one by lambda r infinity Z square 1 by 1 square minus 1 by 2 square. That R infinity and Z is 1 for hydrogen atom. Here we would be having 1 minus 1 by 4. We can write it H here. So 3 by 4 R infinity. Now wavelength for Balmer line for hydrogenic atom is given by 1 by lambda HA R dash Z 1 by 1 square minus square. That means 6 square 1 minus 1 by 4. Here we would be having R dash equals to 36 into 3 by 4. Now, in general, R dash is given by mu e की power 4 pi epsilon naught whole square h cube by c. In case of R infinity, that is m e की power 4 pi epsilon naught square h cube c. Now mu here is defined as m1 m2 divided by m1 plus m2. Here we can say it me into m of ha. In denominator we can write it m of ha because me is negligible. So mu can be replaced with me, and if we replace with me here, so R dash would be equals to me e की power 4 pi epsilon naught square h cube c, which is equivalent to nothing but R infinity. So my wavelength of lambda hydrogenic atom would be R infinity 36 into 3 by 4. And for hydrogen atom 1 by lambda R infinity 3 by 4. Dividing 1 by this 1 by lambda h into 1 by lambda ha, we would get R infinity 3 by 4 divided by 36. 3 R infinity by 4 give us lambda ha by lambda h is equals to 36 implies lambda ha is equals to lambda h by 36. Lambda h is from the problem 656. 56 divided by 36 nm, and so lambda ha turned out to be 18.2 nm. That means our option is correct. In this problem, we are provided psi is equals to 1 by root 6 100 plus 1 by root 3 210 plus 1 by root 2 3 1 minus 1. Now the question is saying you have to determine the probability of particle in state T2. However, initial measurement was done for LZ, and which state that in a measurement LZ for electron in this state, the result is recorded to be 0. So our wave function would be having a form like LZ psi would be dependent only on 0 state. That means I can write it for you psi dash, which is having a form 1 by root 6 100 plus 1 by root 3 210. Now this is a form. So my new wave function, it is this psi on which measurement of energy is carried out. 0 0 plus 1 by root 3 210. Now we can normalize this wave function. So for normalization, psi dash would give us a square 1 by 6 100 100 plus 1 by 3 210 210 equals to 1 implies a is equals to root 2. So my normalized wave function would be psi dash root 2 1 by root 6 100 plus 1 by root 3 210. That means 2 by 3 10. 1 by 3 100 plus root 2 by 3 210. Now probability of having the state N2 which gives energy E2 would be 2 root 2 by 3 I can write it down 5 to psi dash mod square. That would give us root 2 by 3 psi 210 210 mod square is equals to 2 by 3. In this problem, we have to determine the differential scattering cross section for in first born approximation for the potential VR is CR square. Difference scattering amplitude in first born approximator will be given by this term. Substituting the value of potential, we will be having h square q r c by r square sin qr dr limit is 0 to infinity. This integral takes the form of mu c h square q 0 to infinity sin qr r. I will be multiplying here q here and q in the numerator, so I would be getting it 2 mu c h square q. Now I would be taking qr is equals to x, so q dr would be dx. This integration takes the form 0 to infinity sin x by x dx, which gives us 2 mu c h square q pi by 2. So my differential cross section would be, scattering amplitude would be this, and differential cross section would be mod square of f of theta. That means mu c pi by h square q. That means my sigma theta is dependent upon 1 by q square, which means my option A is correct. In this problem, we have been provided perturbed potential Fs in the form of Dirac delta function. And question is asking to determine the first order correction for ground state or excited state. So ground state wave function would be root 2 by a sin pi x by a, and psi 2 would be root 2 by a sin 2 pi x by a. Now first order correction would be in ground state is given by psi 1 h dash psi 1, which can be written as 2 by a epsilon lambda x minus a by 2 sin square pi x by a dx 0 to a. That will give us result 2 by a epsilon sin square pi a by 2 is equals to 2 epsilon a, because a would cancel out, sin pi by 2 would be 1. Similarly, E21 would give us psi 2 h dash psi 2 2 by a 0 to a epsilon delta x minus a by 2 sine square 2 pi x by a dx would give us 2 epsilon a sine square 2 pi by a by 2. Here this would give us pi, so that value would be 0. We have been using this property delta x minus a f x is equals to f of a. So the correct option for this problem would be option B. In this problem, we have been provided configuration of 4 particles of mass m and 4m, and we have to determine till configuration for which particle is having lowest energy in ground state. So let us determine the energy corresponding to mass m and 4m having potential Vx half k square. So I would be considering case 1, case first, that means mass m, and here you would be having it Vx is equals to half kx square, that means half m omega square x square, that means put Hamiltonian is having the form of p square by twice m to half m omega square x square. So for this system, for this Hamiltonian H1, energy of the particle, I would be writing m. M denotes for the particle of mass m would be having the form n1 plus 1 by 2 h cross omega. So em0 denotes the ground state energy for the particle having mass is h cross omega by 2. em1 first excited state for the particle of mass m would be 3h cross omega by 2, and similarly second excited state for the mass m would be 5 by 2 h cross omega. Now we consider the case second. Particle is having mass 4m, that means Vx would be having the form of 1 by 2 kx square, that means 1 by 2 m 2 omega square x square, and Hamiltonian will be p square by twice m plus 1 by 2 m 2 omega square x square. Energy for the particle in this case, where 4m is subscript for the particle 4m, would be n2 plus 1 by 2 h cross omega. So that can be written as into 2h cross 2 omega, not omega. So this can be written as 2n2 plus 1 h cross omega. So ground state first excited state energy, ground state energy for this particle will be h cross omega. First excited energy would be 3h cross omega, and second excited state energy would be 5h cross omega. Now we just see the distribution of particles, these 4 particles according to the question. Mass m, mass 4m, E0 would be h cross omega by 2, E1 would be h cross 3h cross omega. Three h cross omega by 2, E2 would be 5h cross omega by 2. Here that would be 5h cross omega, 3h cross omega, simply h cross omega. Now consider the first case. First case, 4 particles of mass m. That means case first, 4 particles mass m. That means energy would be E0 would be 2 into h cross omega by 2 plus 2 into 3h cross omega by 2 is equals to 4h cross omega. Now, case 2, 4 particles of mass 4m. Now, in this case, distribution would be now energy of the particle will be 2 into h cross omega plus 2 into 3h cross omega. That would be 8h cross omega. Now, case 3, 1 particle of mass m, 3 particles of mass 4m. 1 particle of mass m and 3 particles of mass 4m. Distribution in this case would be 1 is here, 2 particles would be here, 1 is here. So ground state energy would be h cross omega by 2 into 1 plus 2 into h cross omega plus 1 into 3h cross omega. That means energy would be 5.5 h cross omega. Case 4, 2 particles of mass m and 2 particles mass 4m, like this. Energy in this case would be 2 into h cross omega by 2 plus 2 into h cross omega. That gives us 3h cross omega. We can say 3h cross omega is lowest. So our option would be D.